Today, friends, we'll uncover the secrets of a world unlike any other. Welcome to the most extreme planet in the solar system. Living next to the sun is no easy task. Scorching, incredibly high temperatures, deadly radiation piercing through space, and continuous collisions with various meteors hardly make Mercury the most hospitable region of our solar system. As one can easily imagine, these immense challenges make the planet particularly difficult to explore and reach. It is for this reason that, despite Mercury being significantly closer to us than gas giants like Jupiter or Saturn, it remains a relatively unexplored and mysterious object. Nevertheless, despite all obstacles, scientists have successfully carried out two different missions designed to study Mercury in detail. The first was the Mariner 10 spacecraft, which flew past the planet in the 1970s. It was followed by NASA's Messenger probe, launched in 2004, which became the pioneer to successfully orbit the planet. And now, a third mission to Mercury is currently speeding through the starry expanse of the constellation Pisces, more than 177 million kilometers from Earth. This project, known as BepiColombo, is a joint effort by the European Space Agency and the Japan Aerospace Exploration Agency. It is expected to arrive at its destination on December 5, 2025. Its task is to conduct a comprehensive and in-depth study of Mercury's magnetic field, surface, and internal structure. However, as ancient wisdom states, the journey itself is the goal, and BepiColombo's journey is long and winding. On October 20, 2018, BepiColombo began its epic journey, launching from the Kourou spaceport in French Guiana. This marked the start of its 7-year marathon to Mercury. Its carefully planned trajectory involves 18 orbits around the Sun, including 9 planetary gravity assist maneuvers. The first of these was an extremely close flyby of Earth on April 10, 2020. At that moment, BepiColombo approached our planet's surface to a distance of only 12,700 kilometers, roughly equivalent to the distance from Copenhagen to Santiago, Chile. Its path will then include 2 flybys of Venus and a remarkable 6 flybys of Mercury itself. The last 3 of these are scheduled for September, December, and January of next year. In total, this mighty spacecraft will travel a colossal 8.5 billion kilometers. Choosing such a long and complex route was the only way for BepiColombo to slow down sufficiently before approaching Mercury's orbit. But a natural question arises: why is deceleration so critically important? If the spacecraft arrived at the planet with excessive speed, it would simply fly past it, and instead of entering orbit, would inevitably be pulled into the Sun's powerful gravitational field. BepiColombo was designed to complement and expand upon discoveries made by its predecessor, the Messenger probe. Although BepiColombo carries many of the same scientific instruments as Messenger, it is equipped with more sophisticated and advanced tools capable of collecting significantly more data. Furthermore, Messenger's orbit around Mercury was rather one-sided, with its pericenter located over the South Pole. This meant we obtained detailed data and maps of the Northern Hemisphere, while information about the Southern Hemisphere was virtually non-existent. BepiColombo aims to rectify this situation by exploring Mercury from an orbital angle that will be more aligned with the planet's equator. BepiColombo is a highly unique and complex spacecraft. It consists of 3 main parts: 2 orbiters and a propulsion module, which were launched and are traveling together in a single configuration known as the Mercury Cruise System, managed by the European Space Agency. The Mercury Planetary Orbiter, MPO, will focus on studying the planet's surface and internal structure. Meanwhile, the Mercury Magnetospheric Orbiter, MMO, developed by JAXA and affectionately known as MEO, will concentrate on investigating the planet's suspiciously weak magnetic field, which has puzzled scientists for decades. The name MEO was chosen by the Japanese public. It means waterway, and according to JAXA, symbolizes both scientific milestones already achieved and wishes for safe future journeys. MEO and MPO are positioned on either side of the interplanetary propulsion module, called the Mercury Transfer Module. This arrangement means that most, but not all, of the scientific instruments on board will be inactive until BepiColombo enters its operational orbit around Mercury. At that point, The MPO and MEO will separate from the spacecraft and embark on their individual paths to study Mercury from different vantage points. But there's no need to worry. There will still be plenty of data to keep us informed of all new discoveries. Let's look back to assess how far this mission has progressed, what it has already taught us, and explore some of the amazing things it has seen along the way. BepiColombo's first significant encounter with Mercury occurred in October 2021. Flying just 200 kilometers above the surface of this enigmatic planet, it transmitted truly captivating images back to Earth. During its swift flyby, BepiColombo meticulously captured Mercury's northern hemisphere. To the untrained eye, these landscapes might appear similar to our rocky and seemingly inert moon, but to the experienced observer, there is much more to discover. Calvino crater is visible, which scientists believe may contain key data to unravel the chemical composition of Mercury's crust. Lamonto crater, on the other hand, holds traces of ancient volcanic activity in mysterious cavities where an unidentified compound, part of the planetary crust, inexplicably vanishes into space, and the scientific community currently has no idea how or why this happens. These astonishing images serve as a vivid reminder of how full of mysteries Mercury is, and how much we still have to learn about it. Another camera on board the spacecraft offered a completely different perspective of Mercury, fully showcasing its rich volcanic history. These images clearly show Hayden Crater, once completely flooded with lava and over 250 kilometers wide, as well as Pompu Facula, one of many bright spots on Mercury's surface, presumably formed by volcanic eruptions billions of years ago. While the previous Messenger mission had already unveiled Mercury's volcanic past, it is still astonishing that this ancient activity left such a noticeable and visible trace after such an unfathomable amount of time. And BepiColombo didn't just show us what this flyby looked like, it essentially captured how this flyby felt. It is known that every modern smartphone has an accelerometer that helps the device determine changes in its orientation. Scientists installed a similar device, a kind of accelerometer, on board BepiColombo's Mercury Planetary Orbiter, MPO. This instrument measured the spacecraft's movements and vibrations as it approached Mercury, creating a unique sound map of the flyby. The collected data was then converted into frequencies perceptible to human hearing. Thus, we have the unique opportunity to literally hear this flyby. Pay attention to two distinct sounds that occur at the very beginning of the recording. They symbolize changes in solar radiation pressure as the spacecraft first enters and then exits Mercury's shadow. A loud thump at the end of the recording signifies the moment when the Phoebus instrument moves into its parked position. Quite impressive, isn't it? However, there's another example, and it's even more astonishing. During its flyby, BepiColombo also collected data on the planet's magnetic field, which was subsequently decoded and sonified by scientists working on Earth. This audio file is somewhat more abstract than the previous one, but we will try to explain it. The listener will simultaneously hear two synthesizers. The first synthesizer changes its pitch based on the alteration of the background magnetic field's magnitude. The lower the tone, the higher the magnetic field's intensity. The second synthesizer varies its pitch according to changes in the magnetic field's magnitude. A more turbulent magnetic field is represented by a faster change in pitch. A dashed vertical line indicates the point of closest approach. After reaching this point, the listener will discern something resembling DJ scratching, many rapid changes in pitch. This signifies the moment the spacecraft crosses the magnetosheath, a region where the magnetic field is extremely turbulent. On June 23, 2022, when BepiColombo had traveled just over halfway through its planned journey, it once again approached Mercury. This time, the spacecraft turned its gaze toward Mercury's largest impact crater, the Caloris Basin. With a colossal 1,050 kilometers in width, it is one of the most extensive known craters in the entire solar system. The Caloris Basin likely formed from a collision with a comet, asteroid, or other celestial object approximately 3.9 billion years ago. Highly reflective lava craters on its floor are clearly visible as a bright semicircular area on Mercury's disk, located beneath the magnetometer boom. The second flyby provided us with magnificent images of Mercury's craters that had never been seen before. For example, this image of Hyani crater, located within smooth volcanic plains, possibly near an ancient volcano that BepiColombo plans to investigate in detail once it finally enters a permanent orbit around the planet. Almost exactly a year later, on June 19, 2023, BepiColombo again approached Mercury, flying at an altitude of just 263 kilometers. Images obtained during this flyby captured the 600-kilometer-long Beagle Rupes, one of many low-bat scarps present on Mercury, which was first photographed by Messenger in 2008. Besides our moon, Mercury is the only planetary body in our solar system known to exhibit such a unique tectonic feature. When the interior of a planetary body cools, it leads to global contraction, manifested on the surface as thrust faults, also known as low-bat scarps. Beagle Rupes has a particularly pronounced curvature, exceeding that of other scarps on Mercury, which provides geologists with a rare opportunity to deeply study the planet's tectonic history. As a result of the third flyby, a large impact crater with a central ring, 18 kilometers in diameter, was officially named Manly, in honor of the prominent 20th century artist Edna Manley. The floor of the original basin was flooded with lava, which gave the crater its noticeably smooth interior texture. BepiColombo will continue its thorough investigation of Manly crater from orbit, aiming to measure its carbon composition and identify other potential minerals to gain a more complete understanding of Mercury's geological history. During its recent close approach to Mercury, which was the last in a series of such maneuvers, the BepiColombo spacecraft captured a series of farewell images of the planet. At a distance of just 236 kilometers from the surface, the probe seemed to be bidding farewell to Mercury. Scientists on Earth will have to wait another 16 months before they can receive a new batch of images. These flybys serve not only for the aesthetic pleasure of researchers, but also for obtaining valuable scientific information. They have revealed important details regarding the planet's partial environment and its magnetic boundaries. Among the many instruments on board the MPO probe, Phoebus stands out, which is designed for probing the Hermian exosphere by ultraviolet spectroscopy. Phoebus uses ultraviolet emissions from Mercury's exosphere, which is the outermost and only atmospheric layer of the planet, to determine its chemical composition, structural features, and interaction with the surface. The instrument achieves this by detecting specific types of light emissions in the ultraviolet spectrum, covering a range from 55 to 350 nanometers. By collecting these light signals across the spectrum, Phoebus helps scientists discover what the exosphere is made of and how its particles are distributed. When BepiColombo emerged from Mercury's shadow, Phoebus detected the presence of hydrogen and calcium, confirming earlier data from Messenger, which had already established the presence of calcium in the planet's exosphere, especially near the equator and on the night side. Interestingly, this distribution is opposite to what is observed for sodium and potassium, which tend to concentrate around the poles. After successfully entering Mercury's orbit, Phoebus will be able to provide a much more detailed analysis of the exosphere, its composition, and its dynamics, including how it changes with geographic location and time. Speaking of Messenger, it's worth recalling that it once discovered ice near Mercury's North Pole. BepiColombo will continue this important legacy, continuing the search for ice in the permanently shadowed crater regions located at high latitudes. As is known, Mercury is the only planet in our solar system with a magnetic field similar to Earth's. Thanks to its liquid iron core, Mercury exhibits a dynamo effect, which leads to the formation of an internal magnetic field around the planet. However, Mercury's magnetic field is only 1.1% of Earth's magnetic field, which sparks immense scientific interest in its generation mechanisms. One of BepiColombo's main objectives is to gain a deeper understanding of this magnetic field. Until now, only the Northern Hemisphere's magnetic activity was mapped by NASA's Messenger mission. Scientists hope that BepiColombo can shed light on the planet's magnetic dynamics in the Southern Hemisphere. This magnetic field is of immense significance. By understanding it, researchers aim to unravel the mysteries of Mercury's origin, its evolutionary path, and the current state of the planet's interior. The MPO and MEO will traverse different regions of Mercury's magnetosphere across various timescales, simultaneously measuring how the magnetic field changes in time and space and its interaction with the powerful solar wind. All this new data obtained during the BepiColombo mission will ultimately be compared with global magnetic field models created by the MESSENGER mission to construct the most accurate picture of Mercury's magnetic field to date. This could reveal important insights into the elusive past of the planet. As we await BepiColombo's next flyby, scheduled for September 2024, the journey to understanding Mercury continues. The spacecraft is preparing for its next major maneuver, a long arc of solar electric propulsion engine operation, which is set to begin in early August and last until mid-September. Thrust arcs, along with strategic flybys, help BepiColombo counteract the Sun's immense gravitational pull. This is the only way to successfully enter Mercury's orbit when the time comes. After orbit insertion in December 2025, the real exploration will begin. Mercury's heavily cratered surface holds 4.6 billion years of asteroid and comet bombardment history, which, combined with unique tectonic and volcanic features, will help scientists unravel the planet's place in the evolution of the solar system. The BepiColombo spacecraft is scheduled to remain in orbit around Mercury for 1 year, and if all goes well, it may be approved for an additional year of mission. Scientists have high hopes for this research, aiming to study the planet in unprecedented detail, from its chemical composition to its geophysical features, from its tenuous atmosphere to its magnetosphere, and to shed light on its history and the evolution of other inner planets, including Earth. Until then, we can look forward to several more flybys and, undoubtedly, captivating images that will be captured for us, the inhabitants of Earth. Imagine yourself standing on Mercury's surface, but not the Mercury you typically envision. This is not a sun-baked daytime inferno. Instead, you are here during the planet's incredibly long night. The sun set weeks ago and won't rise for many more weeks. Above you, the stars are bright and brilliant against a perfectly black backdrop, untouched by atmospheric haze. The ground beneath your heavily insulated boots is firm, radiating the day's heat into the vacuum of space. It is a quiet, desolate landscape. But tonight, you've brought special equipment, not just for survival, but for observation. You point a sensitive detector, tuned to a specific wavelength of light, toward the anti-solar point in the sky, the direction directly opposite where the sun hides below the horizon. And you see it. Something faint, ethereal, almost unbelievable. Stretching from the planet, extending incredibly far into the blackness, is a ghostly, elongated glow. It's a whisper of light, invisible to the naked human eye. A delicate structure millions of kilometers long, trailing behind this tiny, battered world like the train of a ghostly gown. Mercury, a seemingly inert little rock, the closest to the sun, is doing something profoundly strange in the dark. It's ejecting a tail into space. A tail not made of gas or dust, as we typically imagine comet tails, but of something far more specific and intriguing: sodium atoms. When we think of planets with distinctive features, Mercury rarely comes to mind. It's the outcast of our planetary family, a tiny, cratered world baking under the sun. But in 2001, everything changed. Scientists had been using specialized sodium filters to observe Mercury since the mid-1980s, when sodium was first detected in the planet's exosphere. This is what a team at the McDonald Observatory in Texas was doing when they noticed something strange: a faint glow extending far beyond Mercury's tiny disk. Initially, they couldn't believe their eyes. They thought it must be the result of equipment malfunction or data processing errors. But after rigorous checks and rechecks, the astonishing truth was revealed. Mercury was leaving behind a vast structure in space, a tail of sodium stretching nearly 2.5 million kilometers behind it. For comparison, that's 700 times the width of Mercury itself. The discovery was stunning. Mercury isn't some distant, obscure object. It's one of our closest cosmic neighbors. We've observed it since ancient times and even visited it in the 1970s and 2000s, thanks to NASA's Mariner 10 and Messenger spacecraft. Yet, This colossal feature remained completely unnoticed until the 21st century. This discovery was a significant event because it challenged our classification of what can have a tail in our solar system. Suddenly, Mercury wasn't just a boring, cratered world, but a planet with a dynamic feature rivaling the most spectacular comets. So, how does Mercury's tail differ from comet tails? And why would this planet specifically have a sodium tail? The answer is a fascinating result of Mercury's unique position, its composition, and the strong influence of the Sun. Comets are a kind of snowball flying through space. They are mainly composed of ice, which sublimates as the comet approaches the Sun, leaving behind a trail of ionized gas and dust particles. In contrast, Mercury is a rocky planet with minimal, if any, ice. Scientists believe that ice may be hidden in permanently shadowed craters at its poles, but these frozen deposits remain stable precisely because they never receive direct sunlight. Thus, Mercury's tail is not formed by the sublimation of ice into gas, it is composed of sodium. But why? To unravel this mystery, one must delve into Mercury's unique position relative to the Sun. At its closest point to our star, known as perihelion, Mercury approaches the Sun to within 47 million kilometers. In this region of space, it is subjected to solar radiation whose intensity is 10 times greater than what we experience on planet Earth. On top of that, the solar wind here possesses truly swift power. Imagine an incessant, unstoppable stream of charged particles hurtling at 1.6 million kilometers per hour directly from the Sun and impacting Mercury. Upon collision, these particles literally knock other atoms off the planet's surface in a process called sputtering. To illustrate, imagine several magnets attached to your refrigerator door. They stay in place and don't fall off on their own due to the magnetic field. But if, for example, you throw a bouncy ball at the refrigerator, upon impact, the energy spreads and dislodges some of the magnets. If the energy reaching the weakest magnet is greater than the force holding it, it will bounce off and fall. The same cascade of collisions occurs during sputtering. Solar wind ions literally bombard Mercury, generating high-energy impacts that knock the least bound atoms off the planet's surface. This is analogous to the bouncy ball knocking the weakest magnet off the refrigerator. And as it happens, one of the least bound elements on Mercury's surface is, you guessed it, sodium. Data from the Messenger spacecraft indicates that during periods of increased solar activity, these solar wind particles, by colliding with Mercury's surface, lead to a 50% increase in the amount of sodium ions in the planet's atmosphere. This fact suggests that enhanced solar activity intensifies the interaction of particles with the surface, which, in turn, leads to a significant ejection of sodium into Mercury's exosphere, and consequently, into its tail. However, this is only part of the explanation. In addition to the solar wind, Mercury is also constantly bombarded by micrometeorites. In the absence of a dense atmosphere to slow their descent, even the smallest dust-sized particles impact the planet with immense destructive force. These tiny space rocks vaporize surface materials upon impact, releasing even more sodium atoms. Essentially, we are witnessing a continuous process of cosmic erosion. The planet is gradually eroding over billions of years, right on our cosmic doorstep. Some researchers have noted enhancements in the tail that appear to correlate with periods when Mercury is thought to pass through denser streams of interplanetary dust, such as debris from Encke's comet. This circumstance would lead to an increased contribution from micrometeorite impact-induced vaporization, temporarily raising the amount of sodium ejected into the exosphere and then into the tail. However, the formation of the sodium tail is not so much due to the solar wind pushing it back, as largely happens with a comet's ion tail. Instead, the dominant force shaping Mercury's sodium tail is solar radiation pressure. This is a subtle yet extremely powerful effect. Photons, despite having no mass, carry momentum. When a sodium atom in Mercury's exosphere absorbs a photon of light, it receives a tiny nudge in the direction the photon was traveling from the Sun. The atom then quickly re-emits the photon in a random direction, causing, on average, a negligible recoil. However, the sodium atom is immediately ready to absorb another photon coming from the Sun. This continuous process of absorbing solar photons and receiving tiny directional nudges effectively acts as a gentle but constant wind, pushing sodium atoms away from the sun. Imagine countless tiny solar sails, each an atom of sodium, constantly propelled by sunlight. This relentless pressure accelerates the atoms in a direction opposite to the sun, overcoming Mercury's weak gravity and stretching them into the vast, elongated tail structure observed from Earth. Since radiation pressure acts directly away from the sun, the tail reliably points in the anti-solar direction. But, as mentioned, despite its colossal size, this tail is not actually visible to the naked eye. So, how were scientists able to detect it? When sodium atoms absorb external energy, they enter an excited state, meaning their outer electron moves to a higher energy level. When this electron returns to its original, or ground, state, photons are emitted at a precisely defined wavelength of 589 nanometers. The light emitted at this wavelength has a recognizable color that many are undoubtedly familiar with from old streetlights. A similar process continuously occurs in Mercury's tail. However, this tail is not visible to the human eye or to ordinary telescopes. To detect it, astronomers use specially designed optical filters, known as sodium D filters, which selectively transmit light specifically at the 589 nanometer wavelength. These filters effectively block all other wavelengths, allowing the faint but characteristic glow of sodium to become apparent against the deep blackness of space. By excluding other light waves, scientists were able to visualize the sodium tail. Mercury's sodium tail exhibits significant changes throughout its 88-day orbit around the Sun, which is characterized by pronounced ellipticity. When Mercury reaches perihelion, its point of closest approach to the Sun, intensified solar radiation substantially increases the rate of sodium ejection from its surface. It would be logical to assume that the tail would reach its peak visibility precisely at perihelion, as the solar wind and radiation are most intense at this point. However, maximum brightness is actually observed 16 days later. Due to Mercury's highly elliptical orbit, its orbital speed also fluctuates significantly, from 39 kilometers per second when the planet is farthest from the Sun to 59 kilometers per second at its closest approach. Through numerous observations, scientists have determined that Mercury reaches its maximum radial velocity after passing the Sun, exactly 16 days after perihelion. In other words, this occurs when the planet is moving away from the Sun at its greatest speed, creating optimal conditions for the sodium tail to expand and be best observed. But why does higher speed lead to an increase in tail brightness? The answer lies in two words: the Doppler effect. When studying the spectrum of sunlight, we find dark lines called Fraunhofer absorption lines. These lines occur where specific wavelengths of light are absorbed by elements present in the Sun's atmosphere before the sunlight reaches outer space. The Sun's atmosphere, like Mercury's tail, contains sodium, which absorbs all sodium-specific light before that light reaches Mercury. However, the faster Mercury moves away from the Sun, the more the sunlight is shifted, or stretched, by the Doppler effect. This means the wavelength becomes longer, or redder, and the entire solar light spectrum shifts, including the Fraunhofer lines. Thus, sodium-specific light is no longer blocked and becomes available for absorption and scattering by particles in the tail. As a result, the tail becomes brighter, and we gain the ability to observe it from Earth. So, if astronomers want to spot Mercury's tail, they just need to look up at the sky 16 days after perihelion, right? Well, it's not that simple. There are three other key factors to consider. First, Mercury must be at a sufficient angular distance from the Sun in Earth's sky so that it's not swallowed by the dazzling glare of the star. Second, the planet cannot be behind the Sun from Earth's perspective. And finally, Mercury must be positioned at an ideal angle for ground-based telescopes to observe it in the anti-solar direction. Such an astronomical alignment occurs only during strictly defined periods, roughly once every few years. And to think that scientists at the McDonald Observatory discovered it almost by chance, that was indeed a fortunate coincidence. Some of the most spectacular images of Mercury's sodium tail have been captured by observatories using coronagraphs, special instruments that block direct sunlight. This allows the faint glow of the tail to become visible, even when Mercury is relatively close to the Sun in our sky. Each successful observation represents a triumph of astronomical planning and precision. These rare glimpses demonstrate a dynamic that changes dramatically depending on Mercury's position relative to the Sun, stretching, shortening, brightening, and dimming in a cosmic dance governed by orbital mechanics and atomic physics. But this story goes beyond Mercury itself. It has provided an unexpected window into key processes occurring throughout our solar system and beyond. Beyond these circumstances, other significant aspects are observed. First and foremost, this discovery offers us a unique opportunity to gain a deeper understanding of the evolutionary processes occurring with planets. Although Mercury's current rate of surface material loss is so negligible that it cannot significantly alter its appearance within human history. Over billions of years, this process could potentially have a significant impact on the chemical composition of its surface. This occurs through the gradual depletion of sodium and other easily released elements. The knowledge thus gained could be applied to hypothesizing what might have happened to older planets in other star systems, allowing us to better understand their life cycles. Second, and perhaps most excitingly, this discovery has profound implications for exoplanet research. In many star systems, there are so-called hot Jupiters, massive planets that orbit extremely close to their stars. If Mercury can generate a tail 2.5 million kilometers long, then these giant planets likely possess even more spectacular features, potentially losing a significant portion of their mass through similar mechanisms. The detection methods developed for the careful study of Mercury's tail are now actively being applied in the search for similar phenomena around distant worlds. By looking for characteristic spectral signatures of elements breaking away from exoplanets, astronomers can obtain completely new and valuable insights into their chemical composition and environment. In fact, we have already detected similar sodium tails around our own moon, suggesting that this phenomenon may be widespread around airless celestial bodies exposed to the solar wind. Mercury's sodium tail represents an excellent opportunity for in-depth study of interactions between planets and stars across the universe. The better we understand this phenomenon, the more important insights we gain into how stars form and destroy their planetary systems over billions of years. The BepiColombo space mission has already successfully completed 6 rapid flybys of Mercury. According to plans, the spacecraft is scheduled to enter orbit in December 2025, where it will spend at least 1 Earth year studying Mercury's internal composition and its impressive exosphere, promising new and exciting discoveries about this amazing phenomenon. Mercury's elusive tail serves as a reminder that even after centuries of astronomical observation, fundamental discoveries are still being made about our nearest cosmic neighbors. What other mysteries might be hidden in our cosmic corner? The universe never ceases to amaze us. All we need to do is keep looking up at the sky. Everyone knows the name of the first planet in our solar system. Mercury was observed since ancient times and bears the name of a Roman god. We have known of its existence for thousands of years. It is not hidden in utter darkness. On the contrary, thanks to its position next to the Sun, it is literally bathed in bright light. Yet, it is the least explored terrestrial planet, visited by only 2 probes in the entire history of our spaceflights. Why is this so? Is it truly that boring? What do we actually know about Mercury? What are its characteristic features and history? And how did we even learn about it? When you think about Mercury's physical characteristics, I'm sure you envision it as the closest planet to the Sun, but also as this giant rock silently drifting through space. You wouldn't be far off in your perceptions, but it's far more interesting than you might initially think. For example, when I look at Mercury, I'm reminded of our moon. However, Mercury is actually visually more appealing than our moon. Look at it in its true color. The first thing I notice is that it actually has color. It's not just varying shades of gray. What else? Well, for instance, did you know that Mercury is composed of approximately 70% metallic and 30% silicate materials? Thus, it is actually more metallic than rocky. Because of this, Mercury's density is the second highest in the solar system, 5.427 grams per cubic centimeter, only slightly less than the planet with the greatest density, Earth, which has 5.515 grams per cubic centimeter. If Mercury were the same size as Earth, it would mean it would have roughly the same gravitational force on its surface. But at its current size, its surface gravity is only 3.7 meters per second squared. If you compared its gravity to Earth's, it would look something like this. So, Mercury's surface gravity is only slightly less than that of Mars. This fact is quite remarkable, considering the significantly larger size of the red planet, and it eloquently testifies to Mercury's high density. Before we conclude our discussion of Mercury's dimensions, it is necessary to present a final comparison. Mercury with Ganymede and Titan. Ganymede, as is known, is the largest natural satellite in the entire solar system and, by far, the most massive of Jupiter's moons. In turn, Titan holds the honorable position as Saturn's largest moon and is the second largest moon in our planetary system. These two giant moons, as is clearly visible, surpass Mercury in size, yet their mass is significantly less. A close look at Mercury's surface reveals a striking resemblance to our own natural satellite, the Moon. It is marked by vast plains resembling lunar Maria and characterized by intense cratering, which serves as compelling evidence of its geological inactivity for billions of years. Nevertheless, it is evident that at some point in its history, the planet experienced a period of geological activity, as indicated by one of its most distinctive surface features, the presence of numerous narrow ridges, some extending for hundreds of kilometers. We will delve into this aspect in more detail later. One of the most remarkable features, impossible to miss on Mercury, is the colossal impact crater known as the Caloris Basin, with an impressive diameter of 1,950 kilometers. The collision that created the Caloris Basin was so grand that it triggered massive lava eruptions and formed a concentric ring over 2 kilometers high, surrounding the impact crater itself. Directly opposite the Caloris Basin lies a vast area of unusually hilly terrain, aptly named the Weird Terrain. Comparing this area to the rest of Mercury's surface makes it perfectly clear why it earned such an unusual designation. So, what is it like to be on Mercury's surface? First and foremost, it should be noted that the temperature on the planet's surface exhibits colossal fluctuations. It can vary from minus 73 degrees Celsius to over 400 degrees Celsius. However, in the polar regions, the temperature never rises above minus 93 degrees Celsius, which is explained by the complete absence of an atmosphere capable of retaining heat. This means there is a very significant temperature difference between the equatorial and polar regions. These changes are also due to the planet's orbital and rotational characteristics, which we will return to later. At the subsolar point, where the sun's rays fall directly, the temperature reaches approximately 400 degrees Celsius, while on the planet's dark side, the average temperature is minus 63 degrees Celsius. Since Mercury is too small and hot, its gravity cannot retain any significant atmosphere for a long time. Consequently, it cannot accumulate the heat received from its close proximity to the sun, which results in the planet's dark side being significantly colder than the side facing the star. Nevertheless, Mercury does possess an exosphere, which is an extremely tenuous atmosphere-like volume surrounding the planet. The molecules in the exosphere are gravitationally bound to the planet, but the density is so low that it cannot behave like a gas because the molecules do not collide with each other. In the presented image, Mercury's exosphere, captured by the MESSENGER probe, can be observed. When the solar wind impacts the planet, it rips certain atoms from the exosphere. What remains is a plume of atoms streaming into space. This phenomenon we call a planetary tail. And every planet, to some extent, possesses such a tail. Even Earth has an exosphere, but it begins 600 kilometers above the surface. This is truly the point where space and atmosphere merge. In Mercury's case, this exosphere is completely unstable. Atoms are constantly lost and replenished from various sources, which we will discuss in more detail later. NASA has confirmed that craters at Mercury's North Pole contain water ice. Mercury also has something Mars does not: a true magnetosphere, or magnetic field, encompassing the entire planet. Its strength is only about 1.1% of Earth's magnetic field, but this is still enough to deflect most of the solar wind flowing around the planet. Mercury has the most eccentric orbit of all the planets, with its distance from the Sun fluctuating between 46 million kilometers and 70 million kilometers. It might be difficult to imagine, but try. Mercury takes about 88 Earth days to complete one full orbit around the Sun. It also exhibits a 3.2 spin-orbit resonance for the planet's rotation on its axis. This means it rotates 3 times on its axis for every 2 orbits around the Sun. Mercury takes about 59 Earth days to complete one rotation on its axis, which we call a sidereal day. By pure coincidence, this is almost exactly half of its synodic period relative to Earth, which is 116 days. Thus, between Earth-Mercury conjunctions, Mercury completes exactly 2 rotations on its axis. Historically, this was a big problem. Because of this coincidence, we long believed Mercury was tidally locked to the Sun. You see, Mercury orbits close to the Sun, which meant astronomers always had difficulty getting a good look at much of it for most of the year. When it finally came into a good viewing angle from our perspective, we were looking at one side of the planet. 118 days later, we looked again during that favorable alignment for observation and saw the same side. Thus, for them, it indicated that Mercury was tidally locked to the Sun. What astronomers didn't realize was that Mercury had completed exactly 2 rotations on its axis during that time. Only radar observations of the planet showed that it rotates slightly faster than it orbits. This 3-2 orbital resonance means that if you were standing on Mercury, one day from sunrise to sunrise, or what is called a solar day, would last 2 Mercurian years. Standing on Mercury, it would look something like this. You would see the Sun rise relatively quickly. Then, as it approaches noon, it slows down and even begins to move in reverse before continuing its journey towards sunset again. As you can see, this took a full year, meaning that night on Mercury also lasts a year. The Sun begins to move backward in the sky because about 4 Earth days before perihelion, the speed at which Mercury moves in its orbit is equal to the speed at which it rotates. At this point, the Sun's apparent motion remains stationary. At perihelion itself, Mercury's orbital speed surpasses its rotational speed. Therefore, to a person standing on Mercury, the Sun appears to move backward. 4 days after perihelion, the Sun's normal motion resumes. This phenomenon becomes even more apparent when viewing Mercury from an overhead perspective. Twice within a single day, observing from one of its poles, one can notice the Sun pausing for a moment, then resuming its journey across the celestial sphere. Another notable feature of Mercury's orbit is its inclination of 7 degrees relative to Earth's orbital plane. As a consequence, we are only able to observe Mercury transiting across the Sun's disk on those rare occasions when it is positioned directly between us, the inhabitants of Earth, and the star itself. And because its orbit has such a significant 7-degree inclination, such an event occurs approximately once every 7 Earth years. The last aspect we will consider in the context of Mercury's rotation is its virtually zero axial tilt, with the most accurately measured value being just 0.027 degrees. This is even less than that of the giant Jupiter, whose axial tilt is measured at 3.1 degrees. And finally, wouldn't you like to see our Earth from Mercury's surface? Well, here it is, just a couple of pixels wide. This photograph was taken by the Messenger probe several years ago. And with the exception of the youngest members of humanity, every one of us was present in that image. But what exactly was Messenger, and why was its mission so important? Well, let's start with a brief historical overview. When humanity first began sending spacecraft to explore the expanse of the solar system, the first planet visited was Venus, our nearest cosmic neighbor, in 1962. Mars followed in 1965 and then Jupiter in 1973. Only then, in 1974, did it become Mercury's turn, and this sequence itself might seem somewhat unusual. The closest distance between Earth and Mercury is 77 million kilometers. In fact, on average, it is the planet closest to us. The closest distance between Earth and Jupiter is 588 million kilometers, which is almost 8 times greater. And Jupiter was visited again in 1974, twice in 1979, in 1992, in 1995, in 2000, and in 2007. Many missions were sent to Saturn, Uranus, Neptune, to comets and asteroids, while Mercury remained unvisited for 30 years. Was it because it was deemed uninteresting? Did we discover everything there was to know about it with that single first mission? No. The first mission was a flyby, and it only mapped between 40 and 45% of Mercury's surface. In reality, the true reason is that Mercury is one of the most challenging planets to visit in our entire solar system. Why? Well, as mentioned, Mercury resides in a veritable furnace. Due to its close proximity to the Sun, its surface temperature reaches a maximum of 430 degrees Celsius. Therefore, any probe heading towards it must possess exceptional heat resistance. But that same proximity to the Sun means that any probe launched towards it will accelerate faster and faster due to our star's colossal gravitational pull. Using rocket fuel to counteract this would be tantamount to trying to paddle upstream against raging rapids. Fighting the Sun's gravity required too much fuel for a Discovery-class spacecraft to carry. Slowing the spacecraft enough for it to be captured by Mercury's orbit seemed an insurmountable task. It was a matter of weight. Weight is a severe limiting factor when it comes to spacecraft. The heavier the craft, the more powerful a rocket is required to launch it from Earth's orbit, and the more expensive everything else becomes. Scientists strive to make everything as light as possible to reduce these costs. Since fuel takes up precious weight allocations that could otherwise be used for scientific equipment, scientists tried to take only what was absolutely necessary to complete their journey. However, for approximately 30 years, scientists could not devise a way to put enough fuel on a probe for it to slow down enough to orbit Mercury, especially if they also wanted to carry scientific equipment. Therefore, after the success of Mariner 10's flyby missions to Mercury in 1974, 1975, Mercury exploration was temporarily suspended. But in 1985, an orbital mechanics expert named Chen Yen realized there was a way to put a probe into orbit around Mercury that didn't require developing new technology. Instead, she devised a special route through the solar system that would slow it down enough to orbit Mercury with just a few course corrections. Instead of flying directly to Mercury, the orbiter would need a significantly longer path. How long? According to Chen Yen's model, the craft would complete about 15 orbits around the Sun, fly past Earth once, Venus twice, and Mercury 3 times before finally slowing enough to enter its orbit on the 4th pass. All these planetary flybys would be absolutely essential. By flying close to planetary atmospheres, the speed could be significantly reduced by atmospheric drag and the planet's gravity. The entire route would cover a colossal 7.9 billion kilometers and take 6.5 years. Chen Yen's discoveries were not immediately considered, but in 1998, NASA began to show interest in the idea and, convinced of the route's feasibility, launched the Messenger probe in 2004. In 2004, a spacecraft named Messenger was launched, a unique probe designed for detailed investigation of Mercury's surface, space environment, geochemistry, and mapping. Its dimensions were quite modest. It was only about 1.8 meters long and 1.3 meters wide. The spacecraft weighed 100 kilograms. These parameters made it relatively small and light for typical NASA missions, especially when compared to the Juno spacecraft, which is 20 meters long. Messenger was equipped with a powerful engine, an innovative ceramic heat shield designed to protect it from the furious solar radiation, as well as 2 solar panels and a full suite of scientific instruments developed to obtain high-quality images and precise data measurements from Mercury. Scientists had high hopes for this mission, aiming to fully study the planet's surface chemical composition, its geological history, as well as its magnetic field and internal core, among other important aspects. Messenger spent the first year of its space journey completing 1 orbit around the Sun before approaching Earth again. This phase provided scientists with an invaluable opportunity to thoroughly test the functionality of all the probe's equipment on a well-studied astronomical object. The goal was to ensure there were no errors and to make any necessary adjustments to ensure flawless operation going forward. During this check, Messenger took several pictures of Earth and the Moon and also tested its other instruments designed to take readings of our atmosphere and magnetosphere. To the team's great relief, everything functioned perfectly. As the spacecraft continued its journey toward the Sun, Messenger employed a highly ingenious technique to slow its acceleration toward the star. It used its solar panels not only to generate power, but also to harness solar radiation, much like sails on a ship catch the wind, propelling it forward. Solar radiation acting on an object exerts a very slight but constant pressure. And although this force itself is extremely small, due to the immense duration of Messenger's journey, its cumulative effect proved quite significant. Maximizing the use of this physical phenomenon became one of the key ways Messenger was able to significantly conserve fuel and naturally decelerate its movement. The next significant milestone in Messenger's cosmic odyssey occurred in 2006 when it performed its first flyby of Venus. Unfortunately for the scientific community, this moment coincided with a period when Venus was on the opposite side of the Sun relative to Earth, which completely precluded radio communication with Messenger. Despite this, the spacecraft took several photographs of the planet, which were sent to Earth later, but no full scientific investigations were conducted at that time. Nevertheless, in 2007, Messenger flew past Venus again. At this time, another spacecraft, the European Space Agency's Venus Express, was already orbiting Venus. Messenger and Venus Express seized a unique opportunity for collaborative work, conducting the first-ever simultaneous measurements of the planet's particle and field characteristics. But the main event that Messenger was aiming for was yet to come: its encounter with Mercury. Messenger performed its first flyby of Mercury on January 14, 2008, and this event went perfectly smoothly, without any complications. The same could be said for the second flyby. However, during the third flyby, which took place in 2009, an unforeseen situation arose. Messenger unexpectedly entered safe mode, which was specifically designed to protect the spacecraft's systems in case of an error or malfunction. What a disappointment it was to have come such a long and difficult way, only for the mission to potentially fail at one of its final stages. Messenger remained in safe mode for what seemed like 7 hours, a period of immense stress for all the scientists and engineers involved. The issue was that Messenger had to pass through Mercury's shadow during this flyby, meaning it had to rely entirely on its batteries for 18 minutes. As it turned out, something was misconfigured in the power management software. Fortunately, Messenger's computer rebooted once power from the solar panels recharged the battery, and it was able to successfully continue its mission, completing another orbit around the Sun before finally entering a stable orbit around Mercury on March 11, 2011. Messenger entered an elliptical orbit around Mercury, where its distance to the planet constantly changed, alternating between 200 kilometers and 15,000 kilometers. Such an orbit was not chosen by chance. Mercury acts as a kind of giant solar mirror, intensely radiating heat back into space. Staying too close to Mercury was extremely hot for Messenger, even with its heat shield, which was primarily designed to protect against direct solar radiation, 7 times brighter at Mercury than on Earth. Therefore, moving away from the planet every 12 hours gave the spacecraft the necessary opportunity to cool down and prevent overheating. After completing its primary objective, the Messenger spacecraft spent the next 4 years in orbit around Mercury, significantly exceeding all expectations and predictions regarding mission duration, as it was initially projected to last only 1 year. Before launch, scientists hoped Messenger would be able to take at least 1,000 photographs throughout its operational period. However, the spacecraft surpassed these modest expectations, taking over 200 images, which allowed for the creation of a complete high-quality and color map of Mercury's surface, as well as capturing nearby comets and other celestial bodies. By December 25, 2014, Messenger's fuel reserves, which had been so carefully conserved until then, began inexorably drawing to a close. During this period, the spacecraft was only 25 kilometers from the planet's surface. Researchers made a final attempt to extend its orbital life by giving the engines a last thrust. But on April 30, 2015, Messenger completed its long journey, crashing into Mercury's surface. After a voyage that lasted over 10 years and spanned literally billions of kilometers, the spacecraft's mission came to its end. Before its demise, Messenger provided us with a colossal amount of valuable information about Mercury. On board the spacecraft was a whole suite of scientific instruments, including a magnetometer designed for detailed mapping of Mercury's magnetic field. Scientists hypothesize that this field is generated by a dynamo effect in its molten core. On Earth, the planet's rapid rotation and the Moon's tidal influence keep our core liquid. However, Mercury has neither a natural satellite nor such rapid rotation. Nevertheless, it exhibits a highly eccentric orbit, more eccentric than any other planet in the solar system. The Sun's gravitational force increases and decreases as Mercury approaches and recedes from the star. Thus, tidal forces constantly pull and compress the planet, and the resulting friction keeps Mercury's core hot, ensuring the dynamo mechanism operates. Unlike Earth's, Mercury's magnetic field is offset from the planet's center by about 20% of its radius, and the reasons for this phenomenon still remain a mystery to the scientific community. Its magnetic field is only about 1% of Earth's strength, but even this has a significant impact, deflecting a considerable amount of solar wind around the planet. However, due to Mercury's proximity to the Sun, the solar wind pressure here is much stronger than around Earth. Combined with the weak magnetic field, this causes the magnetosphere around Mercury to be greatly compressed towards the planet's surface. Earth's magnetosphere, in contrast, extends many planetary diameters from its surface. Notably, these factors make Mercury's magnetosphere extremely dynamic. What does this entail? First, reconnection events occur around Mercury 100 times more frequently than around Earth. Reconnection events arise when magnetic field lines connect under the pressure of the charged solar wind acting on the planet's magnetosphere. When this happens, several charged particles penetrate the planet's magnetosphere, entering the plasma region in the planet's magnetotail. The flows that can be observed in this simulation in the plasma region are the result of precisely such reconnection events. Another feature of the magnetosphere that Messenger revealed was energetic electron bursts, capable of producing hundreds of thousands of electron volts of energy. During its orbit around Mercury, the spacecraft recorded thousands of such events, and mysteriously, they were predominantly localized in the northern hemisphere and compressed toward the sun-facing side of the planet. This phenomenon remains an active area of scientific research. However, scientists hypothesize that these electrons were accelerated as a result of breakups in the magnetotail and travel along magnetic field lines from the South Pole to the North Pole. Messenger also carried a wide array of spectrometers. Spectrometers play a key role in determining the composition of mineral deposits on the surface without the need for direct sampling. In addition, spectrometers can be used to detect particles in the atmosphere. Mercury does not have an atmosphere in the conventional sense, but, as mentioned, it has an exosphere, which is an extremely tenuous gaseous envelope. It is so sparse that particles within it barely interact with each other. However, what Messenger discovered about the relationship between this exosphere and the surface truly surprised scientists. Mercury, it turns out, is covered in volatile substances. It is not merely a scorched, rocky planet. It appears to contain potassium, magnesium, sulfur, sodium, and chlorine to a greater extent than any other terrestrial planet, and significantly more than on our moon. The fact that its volatile ratios have more in common with Mars than with Earth and Venus completely overturned many theories of solar system formation that existed before Messenger's arrival at Mercury. These volatile substances are irradiated by the Sun, with the intensity of irradiation being stronger at the equator than at the poles, which may explain why on the surface some substances, such as potassium, are more abundant in the northern hemisphere than near the equator. Mercury is significantly hotter around the equator than at the poles. Therefore, potassium there would be heated to such an extent that most of it would be lost from the surface into the exosphere. Now, the exosphere contains many particles that can also be found on the surface, such as sodium, potassium, and other elements already mentioned. This exosphere is by no means stable. The solar wind picks up and carries away many charged particles, and solar light pressure also pushes away many neutral particles. If it weren't for processes replenishing the exosphere, Mercury would lose all of it into space within a relatively short period. Although most substances certainly originate from the planet's surface, it also contains other elements such as hydrogen and helium, which cannot be found there. So where did they come from? As is perhaps known, the Sun consists predominantly of hydrogen and helium. And, interestingly, the solar wind delivers these particles to Mercury. Part of the solar wind actually gets trapped in the exosphere and remains there for some time. As far as we know, this is the only primary source of hydrogen and helium in the exosphere. In the upper layers of the atmosphere, called the exosphere, researchers discovered the presence of calcium, whose behavior remains mysterious. Its concentration is significantly higher on the planet's dawn side compared to its dusk side, indicating an unknown process of its distribution. Magnesium was also detected, actively swept away from Mercury's night side. The existence of a tail for this planet has been known to science for a long time. In the presented images, sodium ions glow brightly, which, as they leave the planet, create an effect that makes Mercury resemble a comet. It is astonishing, but if a person were to observe the night sky on Mercury, they would notice a faint yellow glow, reminiscent of distant city lights on Earth. This tail exhibits seasonal variability. Mercury's eccentric or elongated orbit causes its distance to the Sun to constantly change throughout the year. Accordingly, its orbital speed is also subject to fluctuations. The most intense sodium emission is observed when Mercury is at an average distance from the Sun. In Mercury's exosphere, scientists were astonished to discover another substance whose appearance was completely unexpected: water vapor. Its origin may be linked to passing comet tails or to the ice deposits that the Messenger spacecraft identified in the planet's polar regions. Surprisingly, water ice can survive on this scorching planet, but only at the bottom of permanently shadowed craters, where it is forever shielded from direct sunlight. The Arecibo ground-based radio telescope had previously detected highly reflective regions near the poles, and as images from Messenger came in, these areas precisely matched the permanently shadowed regions at the bottom of vast craters. According to approximate estimates, the volume of water ice discovered on Mercury reaches 1 quadrillion kilograms. While not a giant figure by Earth standards, it could be a significant boon for any future colony on the planet, providing access to such a substantial amount of water. Other astonishing features were also identified on Mercury's surface. Hollows were found everywhere. This is a unique feature of Mercury. Although the exact reasons for their formation are not yet fully understood, they are believed to be the result of sublimation or the evaporation of volatile substances, and their uniqueness to Mercury is explained by its close proximity to the Sun. These hollows appear to be an active geological process, likely among the youngest formations on the planet, and they are certainly not the result of meteoritic impacts. Mercury's surface holds many other mysteries. Ancient dried lava flows are visible, testifying to volcanic activity, as are craters from powerful asteroid impacts that heated its surface. Surprisingly, subtle scarps were also discovered, which are evidence of its gradual cooling. These scarps indicate that Mercury is contracting, and according to Messenger data, its diameter has shrunk by more than 14 kilometers since its formation, significantly exceeding initial expectations. All these discoveries thrilled scientists. However, despite the fact that without the Messenger mission, we would know almost nothing about Mercury, for some reason, this mission did not gain widespread public recognition. Perhaps the European Space Agency's BepiColombo mission, which is already en route to Mercury, will be able to better capture the public's imagination when it arrives at the planet in 2025. Let's now transport ourselves back to a time when the planet was significantly warmer. So warm, in fact, that an important question arises. What happens when a planet melts? For Mercury, this is by no means an idle question. At the risk of being understated, Mercury is an extremely hot planet. Daytime temperatures here reach an incredible 430 degrees Celsius. That's the temperature of some wood fires. Rocks and dust on Mercury's surface are scorched by blistering heat that pushes them to their breaking point. It's not the hottest planet in the solar system. That honor belongs to Venus thanks to its dense atmosphere. But Mercury is certainly among the hottest. Mercury, as we know it today, has actually cooled significantly over the years. Ice is present at its polar caps, and we've already discussed signs on its surface that indicate its contraction over time as its interior cools. So what was it like then? When rock is heated sufficiently, its solid structure breaks down, and it transforms into a viscous, flowing liquid known as magma, with a viscosity 10,000 or 100,000 times greater than water. For reference, this is a viscosity similar to tomato ketchup, though I wouldn't recommend adding it to food. Depending on the rock type, magma forms at temperatures no lower than 600 degrees Celsius, but potentially up to 300 degrees Celsius. Thus, for Mercury to begin melting, we know it must have reached at least these temperatures. Despite the fact that molten rock, known as lava, exhibits significantly less fluidity compared to water, it still possesses the ability to travel impressive distances before completely solidifying and stopping. This phenomenon is explained by the fact that as it cools, the outer part of the lava forms a hardened layer. This layer acts as effective thermal insulation, protecting the internal lava flows and allowing them to continue moving unimpeded. How then did researchers conclude that such processes occurred on Mercury? Key clues are found in geological formations, such as Radit Ladi crater. Scientists estimate Radit Ladi to be a relatively young crater, likely less than 1 billion years old. It features beautifully preserved walls and a floor virtually untouched by subsequent meteoritic impacts. The dimensions of this crater are impressive. Its diameter exceeds 25 kilometers. Notably, the hills surrounding the crater are heavily eroded, while its interior is a perfectly smooth plain. This is no mere coincidence. Initially, the terrain inside Radit Ladi was likely as uneven and eroded as the adjacent hills. The question arises, why is its surface so flat now? The answer lies in lava. When left to itself, lava tends to form the flattest possible surface, much like water in a bowl under the pull of gravity. A similar process occurred here. An asteroid impacted the planet's surface, and the resulting crater was quickly filled with lava. Once the lava cooled, it formed the smooth plain we observe today. But where did this lava come from? There are two main hypotheses. The first suggests that the meteor impact triggered a slow volcanic eruption, where magma from beneath the planet's surface rose through fractures to fill the basin. The second explanation is that the surface inside the crater became so intensely heated by the meteor impact that it pushed the already hot rocky crust to its melting point. Such lava is known as impact melt. Most likely, the true explanation is a combination of both these factors. Now that we realize that surface smoothness is a reliable indicator of lava flows, it suddenly becomes clear that many other craters on Mercury must also have been filled with lava. One only needs to look at Rusta Valley crater, where mountain peaks protrude through a smooth layer of lava, or Copland, or Rachmaninoff. Rachmaninoff crater is of particular interest because it shows clear evidence of lava erupting from beneath the surface towards the crater's center. Note the unusual sinuous cracks forming an irregular circle within the central crater. Such formations indicate that a slower effusion of magma pushed through from beneath the surface, disrupting the plane, then rising and cooling again under Mercury's fluctuating temperature conditions. Here, as in many other impact craters, collisions with celestial bodies triggered deep volcanic activity from Mercury's inner mantle layers. However, lava did not only flow within craters. Let's turn our attention to a valley known as Anchor Vallis. In this location, clear signs of a smooth lava flow are visible, but this time it moves like a river. The lava flowed from a high ground to a low ground until it eventually spilled into an adjacent basin. Such flows ultimately filled vast Maria, occupying extensive areas of the planet and coloring them with the more orange hue we observe today. Scientists began to recognize this characteristic orange color as a reliable indicator of volcanic activity. And from this, a more detailed picture began to emerge of conditions on early Mercury that made it even less hospitable for potential life. Areas like this one, located northeast of Rachmaninoff, were likely formed by volcanic activity. When the Messenger spacecraft flew over this area in 2015, it took detailed photographs and discovered that the surface was covered in fine dust. Upon closer inspection, it became clear what this dust was: volcanic ash, which must have erupted from vents and covered the surrounding area. NASA scientists compared this phenomenon to snow, fiery, scorching, furious snow. Thus, on Mercury, you would have had to contend not only with lava flowing underfoot, but also with burning ash falling from the sky. And these were just the volcanoes. The last indicator of volcanic activity on Mercury points to eruptions so destructive that entire fragments were ripped from the planet. Look at this impressive crater, known as Navoi. It represents more than just the trace of a cosmic impact. When a crater forms on a solid surface that has not been sufficiently heated to a molten lava state, a distinct central peak usually arises in its center. This phenomenon occurs because at the moment the crater walls are suddenly exposed, gravity begins to actively affect all loose particles. These particles rush down the slopes of the newly formed basin towards its center. Upon reaching the center and gaining significant momentum, they collide with rocks and landslides, sliding from the opposite side of the crater. Both sides meet, and all the accumulated momentum and energy force them to continue moving in the only possible direction, upward. A similar effect can be observed much more clearly if a large stone is dropped into water. The water from the resulting void rushes in to fill the emptiness, but then collides with water moving from the other side. This entire process leads to a powerful secondary splash directed upward. However, unlike water, the sand and loose rock of the crater do not level out but form a stable central peak. Depending on the meteor's angle of impact, this peak can be either perfectly circular or perhaps teardrop-shaped. However, the central formation of Navoi crater does not conform to either of these types. When scientists carefully studied it, they concluded that this crater was not the result of an impact at all. Instead, it was carved by the colossal force of an erupting volcano. With a diameter reaching 66 kilometers, the upward explosive force that would have been required to form this crater and scatter its remnants for many kilometers around must have been truly grand. So, there it is, the picture of that era. Meteors falling from the sky and heating the rocks they landed on to their melting point. Volcanoes erupting either slowly, filling the landscape with churning magma forming lakes and fiery rivers, or spewing burning ash into the air. Not that there was any air at all, apart from dense toxic gases released during eruptions. And even the ground one could hypothetically stand on might explode directly underfoot at any moment. This is what that time looked like when the planet was in the process of melting. Mercury is now calm. As far as we know, there are no longer active volcanoes on the planet. Although the sun still scorches its surface, the unbridled fury that raged beneath its surface has now subsided and quieted. Nevertheless, for those who know how to look, evidence of what once was is still present, etched into the geological record. These are the scars that tell the story of its turbulent past. When something is as incredibly difficult to access as Mercury, it is exceedingly difficult to study. This is one reason why in all of human history there have only been 2 missions to Mercury, with another one en route: Mariner 10 in 1974, Messenger in 2011, and BepiColombo, which is scheduled to arrive in 2025. Of these 2 previous missions, only Messenger entered orbit around Mercury, and therefore it is the only mission that has ever provided us with close-up images of Mercury's surface. And, quite astonishingly, some of the formations we've seen on the surface remain unsolved mysteries even after more than a decade, while other formations give us hints at the raw primordial power of the early solar system. So, let's conclude by looking at some of these mysteries and formations and see what answers we can find. When you look at Mercury's surface, several features immediately stand out. First, there's its color. Mercury's color is not actually monochromatic. It's speckled with shades of gray, cream, and beige, with lighter areas and lines. These darker areas are believed to indicate a high graphite content, the same material used in pencils, for example. As for the lighter areas, well, we'll get back to those later. Beyond that, you'll most likely notice craters. Like the Moon, Mercury is covered in craters, as ancient fragments of space debris uniformly impact the unprotected planet. These craters provide a fascinating glimpse into the planet's tumultuous history. You can determine the age of a crater by the sharpness of its edges. Sharp and crisp edges are likely much younger than old, rougher edges that have had more time to erode due to natural processes occurring on the planet. Sometimes, asteroids strike the same location as older impacts, creating overlapping craters of different ages, such as the craters visible here. Astronomers note the distinction between ancient and relatively new craters, which is the first intriguing clue to understanding the nature of Mercury's surface. It is an active, constantly changing terrain. Despite the absence of a true atmosphere capable of causing familiar weathering, it is evident that processes on the planet's surface do not remain static on an astronomical timescale. As already stated, Mercury is gradually cooling, and as it does, its surface contracts, forming scarps several kilometers long. However, Mercury's surface doesn't just wrinkle, it also undergoes smoothing. Clear signs of a landslide have been discovered in one crater. While approximately 90 degrees of the crater wall retained its original shape, the remaining 270 degrees shifted deeper into the crater floor, detached from the rest of the rim under its own weight. Scientists cannot yet explain with absolute certainty why such a phenomenon occurred only with a portion of the crater and not its entire structure. Perhaps the ground in the lower right corner was particularly hard, or was it related to the impactor's angle of incidence? These questions remain unanswered for now, and it is this uncertainty that makes Mercury such a fascinating object to study. There is still so much more to discover. Next, let's consider another curious phenomenon. Speaking of the Moon, crater rays or ray systems have already been mentioned. These thin, spiderweb-like lines radiating from certain craters are also a prominent feature of Mercury's surface, with some extending over 400 kilometers. Their lighter shade indicates that the material ejected from beneath Mercury's surface is less graphitic, or at least has a different chemical composition compared to the surface exposed to solar radiation. However, surprisingly, for some time, scientists could not explain the mechanism behind these spiderweb-like structures. When they conducted experiments varying weight, terrain consistency, and impact speed, they failed to reproduce these patterns in laboratory settings. No matter what they tried, the ejected material always settled in a circular pattern rather than in thin, spiderweb-like lines. For many years, scientists puzzled over this problem, but now it seems the mystery has been solved. In 2018, a scientist named Tapan Sabawala, while browsing the internet, stumbled upon information that a group of students had been able to reproduce the spiderweb-like pattern of crater rays. Sabawala was both excited and puzzled. Why had these students succeeded where other scientists had failed? He realized with interest that this was an example of how scientists sometimes prove to be too meticulous. Before conducting laboratory tests, Sabawala and other researchers always carefully prepared the experiment by smoothing the sand into which their test asteroid would then impact. The students, however, skipped this step, leaving the test surface rough. This explanation became obvious in hindsight, as such an approach more accurately mimics the uneven terrain of an alien planet's surface. And, as it turned out, this was the key to understanding the mechanism of these rays' formation. Crater rays do not depend on impact speed, angle, or crust composition. Their formation is determined solely by the surface's shape and its roughness. Understanding how these lines form truly opens one's eyes to the scale of some of the impacts that pummeled Mercury in its past. Recall that some of these ray systems extend over 400 kilometers, and these were only the relatively small ones. One only needs to look at the ray system emanating from a crater known as Hokusai. These rays were undoubtedly created by an incredibly powerful impact, as their lines extend almost completely around Mercury's surface, whose circumference, incidentally, is 15,000 kilometers. And although not as extensive, the ray system of Ducey crater covers a distance exceeding 1,000 kilometers. While the Moon also has ray systems, they are generally smaller than these Mercurian formations. In fact, one of Mercury's key visual distinctions is precisely these giant ray systems. They vividly demonstrate that one of the formative processes explaining Mercury's unique surface is incredibly powerful bombardments. Because the Sun is so close, objects caught in its strong gravitational pull would strike Mercury with much greater force than Mercury could create with its own gravity. Mercury's gravitational pull is so weak compared to the Sun that Mercury is usually unable to capture objects as satellites. Instead, they simply fly past. This is one reason why visiting Mercury poses such a challenge for spacecraft. However, this does not mean that Mercury cannot stop an object heading towards the Sun. It simply needs to intercept it in its path. However, this explanation proves unable to shed light on the origin of the last highly mysterious formation. One only needs to look at one of the most captivating craters on Mercury's surface, named Apollodorus, and the bizarre radial fractures surrounding it, known as Pantheon fossae. At first glance, an observer might think there is nothing out of the ordinary about Apollodorus crater itself. However, these ray-like fractures radiating from its center appear somewhat unusual. Several very strange features are found here. First and foremost, both the crater itself and the surrounding radial fractures strikingly resemble cracked glass. Glass, as is known, cracks in precisely this manner due to its hard yet brittle properties. As already noted, most other craters studied on Mercury do not exhibit such a pattern. Mercury's crust is not prone to cracking, but instead either pulverizes upon impact, forming ray systems, or simply leaves perfectly circular craters. This aligns with the idea of a looser material composition of its surface. Sand, for example, does not crack upon impact. This type of cracking is not observed in other regions of the planet either. Thus, it becomes evident that something quite unusual is happening here. The question arises, was Mercury's surface particularly cold and hard at the moment of this specific impact, making it more brittle? Nighttime temperatures on Mercury can drop to -180 degrees Celsius. But if so, why did a similar phenomenon not occur elsewhere? At least approximately half of all impacts should occur on Mercury's night side. When researchers look more closely at Apollodorus, the crater that seemingly caused these cracks, they notice something even stranger. Apollodorus is not the precise epicenter of this phenomenon. Although it is located quite close, it does not actually coincide with the center of the fracturing. This could suggest that Apollodorus and the spiderweb-like Pantheon fossae fractures are not directly related. Whatever caused this phenomenon, it may have occurred first, and then was merely struck by an asteroid that fell nearby, but not at its epicenter. But if so, then what caused the formation of Pantheon fossae? Intriguing is the fact that there is currently no precise answer to this question. Evidently, something created this cracked glass form, but without leaving a crater. Could this mean it is the result not of an impact from above, but of something that pushed through from below? Perhaps it is a consequence of immense volcanic activity where magma suddenly pressed upward, cracking the crust. This is merely a hypothesis. Many mysteries still need to be unraveled on Mercury's surface, and many other fascinating insights to gain as science progresses. When the European Space Agency's BepiColombo spacecraft arrives at Mercury in 2025, it will embark on another extensive investigation of this planet, and perhaps then scientists will have answers. BepiColombo will unveil the characteristics of Mercury's magnetosphere and exosphere, and researchers will be able to examine its geology and composition more clearly. But until then, scientists will continue to meticulously study the available data. And for now, Mercury endures, baked in its solar furnace. It has survived there for millions of years and will likely survive for millions more, despite everything the Sun and the solar system can throw at it. The hellish conditions of its environment make it difficult to study, but one cannot deny its resilience, evident in its scorched, crater-pocked beauty. Perhaps one day, humanity will know everything there is to know about the first planet in the solar system, but that day has not yet come. Despite being the brightest planet in the solar system due to its location, much light still needs to be shed on Mercury. Friends, thank you for your attention to our work. Don't forget to subscribe to the channel if you haven't already, and we'll see you in the next video.